Good morning. I'm Lu Zhenxie. I work for Gonghan University as an assistant professor in Department of Food Science. So today I'm going to talk about how to produce tranexamic acid by immobilization of bambusa or kami, phenylalanine ammonia lyase, and electrospin nanofibers. So phenylalanine ammonia lyase (PAL) its EC number is 4.3 1.5, which is ubiquitously occurred in plants, catalyze the formation of tranexamic acid and ammonia. So via the non-oxidative deamination of phenylalanine for the synthesis of thousands of different phenylpropanoic metabolites, such as the well-known flavonoids, anthocyanins, and lignins, and so on. So the tranexamic acid is a valuable phytochemical. It has many beneficial effects on lowering body weight and inhibiting lipid accumulation in human hepatocytes. Green bamboo, Bambusa okami, is mainly cultivated in tropical and subtropical areas. So the bamboo shoot is edible vegetables harvested between April and September in Taiwan. So phenylpropanoic metabolites generated by PAL reaction causes bigger castings and reduce economic value of bamboo shoot. So we study PAL in bamboo and cloned 4 different BOPL genes. We also show PAL is co-localized with lignin. So I devote myself in protein studies. As served in Department of Food Science, I focus on how to produce beneficial phytochemicals by enzyme immobilization. So let me introduce a half old, half fancy method called spinning technique. So this is the machine in my lab. So we have polymer solutions in the syringe and give it high voltage. When the charge repulsion stronger than its surface tension, it will spread out and water evaporate on the collector. It will form the narrow fiber membranes. So electrospinning technique have many applications such as enzyme immobilization, drug delivery, and membrane fixation, new wound dressing, biosensor, food packaging, and so on. So herein we mainly focus on enzyme immobilizations in micro. So the chemical cross-linker is used to conjugate enzymes with narrow fiber carriers so that the enzymes can become insoluble polymer. So compared with free enzyme, immobilized enzymes have many advantages. It can be reused and recycled. It can increase protein stability, tolerating broad range of pH or temperature. We can also conjugate multiple enzymes for cascade reactions. Finally, it's readily separated from the product. So the polymers used in these studies are polyvinyl alcohol (PVA) and nylon 6. So the PVA is a hydrophilic biocompatible compound, and the nylon 6 is a hydrophilic compound. So we mix the cool polymer together for making narrow fibers. So the PVA interacts with nylon 6, becoming insoluble in water. So this is the homemade natural cross-linker. So the get chain is oxidized to get chain polyaldehyde. So it can interact with the amino group of enzyme chitosan to immobilize enzymes on the surface of the narrow fiber membrane. A graduate student in my lab already finished all the experiments. Now we are preparing manuscript to publish it. So I don't want to release all the data in my talk, but only mention about the results of E. coli express BOPL1. So E. coli is the most popular expression sequence in biochemistry lab. It has many benefits such as easy to culture, short life cycles, as well as low cost. So on the right is the recombinant proteins expressed in E. coli. So as you can see, we purify recombinant protein to nearly homogeneous. So now enzymes are ready for immobilization. First of all, we have to prepare narrow fiber membranes. In theory, when diameter of the narrow fiber is smaller, it generates more surface area to incorporate with more enzymes. Several factors can affect the diameters of the narrow fibers, such as the concentration of polymer solution, flow rate, voltage, and distance. So in order to study grid factors in one experiment, we adopt the central composite design (CCD) method. So based on the limitation of our machine, we set up grid factors with 5 different levels and use them to generate 20 different reaction conditions. So and then perform experiments according to these settings to obtain results. So this is the log data of 20 different experiments to study the interrelationship of PLO activity and the diameters of narrow fiber. We plot the results in three-dimensional coordinate access graph based on surface response methodology (RSM). So according to the regression equation, this is the optimal operation conditions for immobilized PAL on electro-spun narrow fibers. So this is the three-dimensional coordinate access graph generated by response surface methodology (RSM). So the red color indicates higher level and the blue color means lower level. So the subfigure A to C, in order to obtain higher enzyme activity, we need to reduce flow rate and increase voltage, and also increase distance. So in the subfigure D to F, in order to obtain with smaller diameter, so we need to reduce flow rate and increase distance. So the voltage has no effect on the diameter of narrow fiber. So taken together, small size narrow fibers show higher enzyme activities. We examine the optimal cross-linker condition, and 2% cross-linker give us the best result. So the over cross-linking may affect PLO structure and decrease its enzyme activity. And then we examine the optimal cross-linking kind, and 9 hours is the best condition. So also, over cross-linking may affect PLO structure and decrease its activity. Then we observe the membrane morphology of narrow fibers by thermal field emission scanning electron microscope. So on the left is the surface of narrow fiber, and on the right is the image of the narrow fiber after cross-linking. So when enzyme incorporate onto the narrow fiber, it becomes thicker and condensed. The optimal reaction temperature and pH of fluid and immobilized VOPL1 were compared. Immobilized VPL can tolerate higher temperature than that of free enzyme. There is no effect of optimal pH between free and immobilized enzymes. And then we compare kinetic parameters between free and immobilized VOPL1. So the Kcat value is the turnover number, and the Kn value means enzyme activity towards substrate. So the Kcat over Kn value is the overall catalytic properties of an enzyme. So as you can see, no significant difference between free and immobilized BOPL1. Next, we examine the recyclability of immobilized BOPL1. So after 6 enzyme reactions, the immobilized enzyme still retain around about 40% activity. In the storage scalability experiment, free and immobilized enzymes were kept at 4-degree refrigerators up to 1 month. So as you can see, the immobilized BOPL1 can maintain higher activity than that of free enzymes. So let me make a simple summary. So immobilized enzyme has better thermal stability and has similar catalytic properties with free enzymes. And most importantly, so immobilized BOPL1 can be reused up to 6 times and retain about around 40% activities. So as a result, electrosphere narrow fibers and natural crosslinkers are suitable for BOPL1 immobilization. Thank you for listening. I'm happy to answer your questions.